Thank you very much. It's wonderful to be here. The title probably doesn't make any sense yet, so my job is to try and make sense of what you have on the screen in front of you. So, over the last 10 years, we've seen networking change a huge amount. Understatement, there's been quite a revolution in networking. And so it's only natural to wonder, so what happens in the next 10 years? And I'm very lucky. I don't have to run networks. I don't get involved in the day-to-day development, so I get time to sit back and think about how things might change. And as a consequence, I thought that I would try and share some of what a group of us have been thinking about happens as a direct consequence of what's been happening in the last 10 years or so. And I see my goal in life is to try and make the internet better, as I'm sure many of you do too, and to think about how to make it evolve faster so that we can have more innovation, more change, more improvement in how networks operate. And I actually think that right now we're a bit of an inflection point. This is what I mean by this sort of part 3, this third phase of SDN. So that presupposes that there was a phase 1 and a phase 2, and you're sitting there thinking, what are those? So I will try and explain what I mean by that. And so I want to give you a quick overview of that, and then explain why I think that this third phase is a direct consequence, an extrapolation of what we've been doing up until now. You've heard people talk about zero-touch networks, self-driving networks. We've heard all of the hype and all the buzzwords. But actually, it's a direct consequence of what we've been doing. What we've been doing is laying the foundations in order to make that possible. And I think that the way that that's going to happen is by the direct application of software engineering techniques, which have been developed by the computer industry directly to networking. We've only just begun to borrow those ideas and apply them to networking. Anyway, while preparing this talk, I was reminded of being on this stage in 2012 for ONS, and I think it was actually in this room, giving a talk about what was called Making SDNs Work. And there were lots of puzzled looks in the room, because this is sort of the beginning of thinking about how we might apply some of these techniques. And one of the things that I'd said was, this is a slide that I use, formally verify that our networks are behaving correctly, identify bugs, then systematically track down their root cause. And this was coming out of work that was really happening in not only at Stanford, but a number of universities, about examining and building formal models based on network state. Because if we wrote the software, we know what we were trying to do. We can actually figure out whether the network is conforming to our original intent. I will come back to this a little bit later. But first, really what I'm talking about is what happens in the next 10 years. Let's make the math easier and say we're in 2020 today. But if we look back 10 years and see how much it's changed, back in 2010, networking was dominated by closed proprietary hardware and software. We know this story. It was like the mainframe business of the 1980s. We were in a period of explosive growth of standards. That's where most of the growth was. By 2010, there were over 7,000 RFCs. This seems like progress, right? But most of those were coming with the intent as a barrier to entry. As John Donovan already mentioned today, and will be sadly missed now that he's leaving AT&T, as you may have heard, he said to me when I first met him, the vendors have a stranglehold over me. My job is to break that stranglehold. And this is really what he was referring to. It had created, ironically, this proliferation of standard into an ossification. This was the term that was used. It was a fancy term, but you could read about it in the newspapers at the time, and the research community was using this term of ossification. Innovation was basically glacially slow. So along came new efforts. There were things like clean slate programs, 4D, that came from AT&T with Albert Greenberg's leadership when he was at AT&T before, and Jen Rexford and others. There was the ethane project that Martin Casado led at Stanford. So something badly needed to change, and of course it has, and we all know much about this. There was disaggregation, there was OpenFlow in the early days, then SDN and NFV, which really came out of that effort, then network virtualization, then more recently programmable forwarding, and then that enabling more telemetry. And sort of throughout this period, open source has grown and been a credible force in networking. So imagine 10 years ago, someone was to tell you that open source would be a strong force in data center networks and in ISP networks. I think you would have snickered, right? You'd have giggled, because it just seemed incomprehensible. Well, we just saw over the last few minutes a description of not only real trials, but commitments to go into deployment. And over the next couple of days, you'll see even more of that. And so we're just at the cusp of a lot of work turning into the realization of that sort of revolutionary goal. So I refer to this as sort of phase one. And this phase one is really about changing who is in charge. The network owners and operators have said, no, we want to be in charge. It's relinquishing control from the equipment vendors and saying, we want to define how our networks behave. So that's largely happened, or it's well underway. I don't mean to say that it stops in 2020, but the momentum has picked up enough that this is really sort of unstoppable at this stage. So actually, now we kind of take it for granted, don't we? That if you own a large network, you can download, modify, buy, commission the software that controls your network. That on its own is a revolution. In 2010, every large hyperscale data center company in the world, their networks were based on proprietary equipment with proprietary software running on proprietary hardware. Today, every single hyperscaler in the US and in China operates on merchant silicon with software they either wrote or got it from someone else. So that's a big change. And now we see through what ONF is doing, that is happening to the network operators, the ISPs as well. And I mean, just stop for a minute and look at the number of projects that we just saw and the amount that's going on from a team of 30 people. And I take my hat off. Yesterday, my contribution to the ONF board meeting was to say, wow. Because the number of projects that are going on from a team of only 30 people, clearly that has to have a large army of other people involved to make that possible. And so this is an immense, immense change that we're seeing happen right now through ONOS, Cord, Trellis, Siebel, Stratum, et cetera. We've seen those projects today. So more recently, we've seen what I refer to as this phase two. And I think of it as a natural consequence of this phase one, which is network owners starting to take control of how the packets are processed as well. Because to understand why this is inevitable, you just have to remember that a network, whether it's a wired network or a wireless or a cellular network, is really just a means of taking a packet from one place and transferring it somewhere else and doing a little bit of processing as it goes by. If you're not in control of the software that defines the behavior of how the packets are processed, then you're not really in control of the network. So again, this is a kind of an inevitable follow-on next stage. And over time, I think that you will see that this will happen more and more. As many of you know, I've devoted the last 5 years to trying to help move this forward through P4 and Barefoot, et cetera. But I think this is part of a bigger trend, and I think that we'll just see this inevitably across NICs, across switches, et cetera, throughout our industry. Right now, we're in the lucky position that we have many of the pieces of technology that we need to build the kind of demonstrators that we've seen described today. And we have P4 now part of ONF as a de facto industry standard for defining forwarding behavior. And both Barefoot, now part of Intel, and Broadcom are both building and have announced that they will build programmable switches. So you can see that this is sort of picking up speed and picking up momentum. Let me just explain a little bit more about why this is happening. 2010, this is what switch pipelines look like. They were fixed function. They did a fixed sequence of operations. So if we look inside the boxes that you would build from that, and we look at the switch OS controlling the switch underneath through a driver, what the switch OS was capable of doing was telling that switch which stages of a pipeline it could use to implement these types of functions like OSPF, BGP. So it would be a fixed function pipeline. Packets would go through. We see the headers on there representing different protocols that would be processed. Now imagine that it's 2010 and you want to add a new feature. Big new feature of the time was VXLAN, a standard introduced by Cisco and VMware. But in order to do that, you needed to actually introduce not only new software, but a new stage in that pipeline. If anyone in the room was to add the software that was to do that, it would take you about 2 weeks. It was a very simple operation. In the silicon, it took 4 years. Why is that? Because it had to go through an entirely new development. And then by the time that development took place, the 4 years before the first silicon showed up, most people had moved on to another kind of standard. So the silicon was way out of step. The evolution of the silicon was way out of step with what the industry needed. What we were really stuck in was this bottoms-up approach, where a data book would tell us, a data sheet would tell us how packets would be processed, and it would be described in ambiguous English. And so that definition was driving what the system could do. You know, our industry has moved on generally from this kind of this model. The computer industry doesn't work this around. We describe at the top what we want. A compiler then maps it down onto a chip. We never actually see what that chip does. We don't know what kind of CPU it is that's running underneath. That's the abstraction that it hides. So now we're starting to see this happen top down, and I think that we'll see this more and more in networking, where we describe a behavior that we want in the control plane, in the management that sits above it, in the forwarding plane, all the way through, and then that will be compiled down, and we won't even know how that gets implemented or gets mapped onto the hardware, whether that's a forwarding pipeline that is dedicated to the purpose, an FPGA, a CPU, whatever it happens to be that's implementing that. The PISA pipeline is what has made this possible initially as the protocol-independent switch architecture, where we have a programmable parser that is told how to process the packets and how to understand what those headers are, and then a pipeline of identical stages that will go through and perform match plus action, where the match is on a memory and the actions are with ALUs, and there are hundreds of these typically inside one of these chips, such that an arriving chip, its headers are split apart in order to once we understand what they are, and then it will go through a sequence of transformations from one stage to another, and we could think of this as a geometric transformation of that set of headers as they go through from one end to the other, until eventually we've finished the serial-dependent processing on that packet, we reassemble it, and then we send it on its way. This is the sort of the forwarding model. It may actually be burned into silicon or not, but this is the forwarding model to think of when you're thinking about processing packets using a language like P4. And when you write that P4 language, it's being mapped down onto either that or an abstraction that works in that fashion. So the reason that I spent the last 5 years, and will continue to do this, on this programmable forwarding is I believe that programmable switch chips can have the same power, performance, and cost as fixed function switches that they will replace, which means, and I like this term, beautiful new ideas, not my ideas, your ideas, beautiful new ideas can now be owned by the programmer, not by the chip designer. So in other words, your ideas find their way into the network more quickly, which means more innovation. And that means a better internet. Just as an aside briefly, you should be skeptical. Skepticism is appropriate. How do we know if a programmable switch chip can have the same power, performance, or cost? Haven't we always been told that that programmability comes at a great expense? So I went and took the numbers from an equipment vendor, who's represented here today, who builds these systems from both the programmable and the fixed, and just took the numbers off their website. I don't do this to try and sell you anything, just to get across the idea that that intuition that we have that it comes at a penalty is actually not the case. It is essentially the same. Let's look at the numbers here. These are for two identical systems built with the same feature set, one from a programmable silicon, one from the leading fixed function. They have essentially the same forwarding rate. They're both built out of 16 nanometer. The 16 nanometer technology kind of divides the forwarding rate here. It's slightly higher, but we can call it the same. The power draw typically is slightly lower for the programmable. That's probably surprising. The latency is slightly lower as well. Why is this? It's just a pipeline. There's not really anything magical to it. It's just a pipeline that you get to configure rather than being fixed. This will actually be the way the future ones are built. So as a consequence, we're seeing programmable forwarding happening now. It's getting used primarily, actually, to reduce complexity. The first thing that we've noticed that people do when they have this in their hands is they throw out the features that they didn't want so that they don't have to use up all the resources in the silicon. That's partly how they get to the lower power. The second thing that they do is they add new features that are specific and private to them. New congestion control algorithms, layer 4 load balancing, middle box functions that they wrap into the network, whatever makes sense to them. Often, you don't know what they're doing because they get to program it themselves. But probably the big one that has been the most common, the most popular, is telemetry. And it's a little bit odd that telemetry becomes possible because of programmable forwarding. Telemetry could have happened before. The problem was no one knew what to measure and where to put the bits that you were measuring in the packets, because in every network it had to be different. Doing that in fixed function silicon was not really practical. You need to have it programmable so that you can choose where you put it in different networks. It's just a sort of a practical consideration. As we know, p4.org is now part of ONF, and there's lots of activities. I hope that you get involved. I particularly wanted to call out 4 people out of the cast of many, many people who have worked on the P4 sort of evolution. Nate Foster, who runs the effort day to day, Amin Vedat from Google, Jen Rexford from Princeton, and Chang Kim from Barefoot. Okay, so phase 1, phase 2, what's the big deal? I actually think the big deal here is that it kind of completes the picture and creates a deeply profound consequence for networking. What we have now done as a community is we've created a programmable platform, top to bottom. And as soon as we have that platform, which we now do, we don't need to think of it in terms of the protocols that were baked in through data sheets and the IETF, et cetera. It's just a programmable platform. We can do with it as we wish. This actually sets us off on a whole new direction if we so choose. If we want to continue to implement the legacy protocols because that's what we need to do, then of course that's what we should do. But we can gradually start to move off in new directions. So I think this actually unleashes really quite a big potential revolution of its own. So, indulge me for a minute. I'm going to kind of wax lyrical about where I think this might take us. This isn't just my thinking. This is from a group of us, including ONF and some other colleagues. But we've been sort of contemplating what actually does this look like? What might this look like in 2030? The first thing is the network is now a programmable platform, top-down, including the control plane and the forwarding plane. But as we look forward, what does that look like? Let's make some extrapolations. Well, OK, this is an easy one. I think that NICs switches, vSwitches, in fact, entire networking stacks will be programmable as defined by the user for over 10 years in 10 years' time. It's happening now. It isn't going anywhere. It's going to grow over time. We will think of the network as a programmable platform. We will describe the behavior that we want at the top. What I mean at the top is not on an individual box level, but at the top of the network as a whole, whether that's a data center, a large network, or a portion of a network, or a mobile operator's network. It will be partitioned. Its behavior will be partitioned in a way that we won't see. Whether a bit gets used in a packet in a NIC or a switch or a vSwitch, I don't want to know that. I don't know how memory gets laid out when I write a program in Java. I don't want to know how those get laid out. Right? We have got to put in place an abstraction that shields us from those kinds of details. It will be partitioned, compiled, and run across different elements. And every large network will, as a consequence, work slightly or significantly differently from the others, will be tailored to the particular needs of those networks. I've already seen networks, large networks, that use source routing. Who would have thought? That use addressing formats that are different from standard, that use congestion control based on signals that no one has ever heard of. So this is already happening at a small level, but this is going to happen on a much, much larger level over the next few years. I think we'll no longer think in terms of protocols. Protocols will be a little bit of a quaint piece of history. They will have been the necessary thing we needed to get going and to bootstrap. But large networks will be programmed to a behavior, and only at the edges where they need to talk to others will they use standard protocols. Sound heretical? Sure. But I actually think that we're already on a trajectory towards that. Many, many networks are already doing this to some extent internally, within a data center, within a region of an operator. This will start to happen more and more. Notice I'm probably the first person to mention the IETF today. As a consequence of this migration of function out of hardware and up into software, this poses a problem for us at the university is, what the hell do we teach networking students? Gone are the 7-layer OSI, how we go through the sort of progression of protocols the way that the textbooks describe today. This is a very exciting challenge. I think we'll describe it to them as a distributed computing platform. We'll give them examples on congestion control and routing and the things that we know, but these will become examples. Routing and congestion control will become programs, partitioned across the end-to-end system by a compiler, and we'll have to get the students used to the idea of using this. But if we really want to go further than that, which is if you're operating a large network, of course you want to do this, how do you get the humans out of the way completely? Because we're always the problem, right? When anything goes wrong, it's almost always human or operator error. So what else do we need? What else do we need to have happen? Because it's not just enough, we don't leave all of our applications, Facebook doesn't leave its application without humans involved in order to keep it running, until you can do something that kind of closes the loop. What does it mean to close that loop? We all talk about closing that loop. But what is that? What actually do we need to do? So I want to put it to you that we need at least 3 pieces. First, we need the ability to observe packets, observe network state, in other words, the state that defines how packets are processed in the network, the forwarding state, and code, all of the code top to bottom. We need to be able to examine that in real time and keep an eye on what it's doing. Because things in networking happen in nanoseconds. No human can keep up with that. We need that completely automated. We need the ability to generate new control and forwarding behaviors as needed, on the fly, it's kind of scary, to correct errors as they've just been observed. Right? We are far from this today. Right? You wouldn't contemplate doing this today. And if we're going to generate something, we better verify it against some original desired behavior or set of invariants to make sure that it's doing what we originally intended, and then get it deployed quickly. I like to use the example of what if I find a packet in a network, or rather some piece of machinery finds a packet in the network. It shouldn't be there. It should be able to figure out, how did it get to be there? What was the piece of code or state or failed hardware that was guilty for allowing it to be there? And let's do whatever it takes, reroute around, install a new rule, change the forwarding behavior, change the control code, set off an alarm maybe, in order to prevent that from happening again. And you better be able to do that in milliseconds, not hours. Otherwise, there'll be a whole load more packets behind it that are then infiltrating the system, or breaking it, or whatever the protection that you're worried about. There's some signs that this is happening, and by the way, what I mean by signs here is mostly in the research community. Of a lot of work that's gone on to this end, In terms of observing packets, there's been a lot of commercial work in this area through INT. So observing packets today, PerPacket telemetry is already starting to happen. And I don't want to tell you that it's somehow super mature and that it's not going to change. It's just beginning right now. I started looking at this because I was very concerned that even basic information about the network's behavior was really, really hard to find. Tracer out, ping, that's kind of about it, right? I actually used that statement in 2012, and it's still true today, right? Nothing has really changed. If you have PerPacket telemetry, then you'll see that this begins to change. What I mean here is, in a network where there are packets flowing, why is it, or why isn't it, that I can just take one of those packets and ask that packet, what path did you take? Not what path did some probe that somebody else sent take? What path did this packet take? There's not a single commercial deployed network at scale that's publicly talked about, at least, that allows you to do this today. It's kind of shocking. How do we debug these systems unless we know that? What I'd like to do is be able to, for the packet to tell me, I visited these switches and at what time I visited them. That tells me how it got here. What if I want to know why it got here? If I'm going to try and close this loop, I need to know why it got here. I need to know the set of rules in the switches that this followed. Every switch knows the rules that it followed. Why doesn't the packet know? So why can't I probe the packet and ask it, which rules did you follow? So that tells me about how it got here and why it got here. Let's think about the performance. I'd also like to know how long did it queue at each of the switches along the way. So for example, I'd like it to be able to tell me that it was delayed by this amount at each of these. The switch knows, because it actually had to keep track of that packet as it went through. Why can't the packet know as well? So here we've got a big red number. That's a problem. I'd like to be able to go to the switch and say, show me the time series of the occupancy of the queue, so that I can figure out not only that there was a problem, but I want to know who that I was sharing that queue with, so I know in this particular case it's the orange flow that was causing the problem, and now I know whose throat to choke, I guess. So this basic information, this rather obvious information, if we're going to try and do this at scale, which path did my packet take, which rules did my packet follow, how long did it queue at each switch, and who did it share the queues with? Yes, that's beginning to happen with P4 and INT, but this is just the beginning. Right? This, I think, will be standard operating procedure in a few years' time, that we'll expect that in a network. I like the picture that, you can jump over this, about INT. Many of you will know how it works. This picture here, this is a picture taken from a financial network of the occupancy of queues using INT as per packet measurement, showing the evolution of a queue in the network with a microburst. The entire x-axis here is about a microsecond. So it captures the entire microburst with every packet event down to the nanosecond. That sort of thing seems kind of science fiction today in an operational network. I think it'll actually be standard. PerPacket examination of what's going on in the network. So if we can observe the packets, can we observe the network state? Well, actually, this is already starting to happen commercially as well. For those of you who are familiar with something called header space analysis, that was first described and published in about 2010, you may know that forward networks, and also Veriflow was doing something very similar, is kind of commercializing this approach today. Briefly, you build a model of the forwarding behavior of every switch in the network based on the program that describes its behavior and the state that it currently contains, that allows you to ask questions like, can A talk to B, and formally prove that it can or it cannot. You would do this by saying, let me consider all possible packets. This is what this cube represents. Let me see how that set of packets would be mapped forward through the network and then backwards through the network, and then see whether it's possible and which packets could communicate. It also allows you to generate a set of tests automatically to test whether the hardware is functioning correctly. And if you find a packet at B that should not have been there, it also allows you to figure out where that fault was. This already exists. Now, it was kind of in the lab. It's in the process of being commercialized. You'll see a lot more of this kind of activity. it's beginning to give us these pieces that we need for automating this behavior. But what about these two pieces? The ability to generate new control and forwarding behaviors on the fly, and the ability to verify newly generated code and deploy it quickly. Let's return to this picture here. We've all seen this picture many, many times before. Sort of the SDN picture. What does it mean that we actually need here? So we need to be able to observe very quickly, to measure and then validate the packets, the state, and the code. The bottom two, there's already progress being made in that direction. The top one, we still need work to do to verify that code. Of course, there's software engineering techniques that are being worked on. We then need to feed that back to how we would change the control plane in order to how to generate new behaviors, new control code, new forwarding code, new state, and verify that it's doing what we intended. So, for example, changing and modifying a control program in the Trellis framework, changing perhaps ONOS state or its ONOS's behavior. Maybe then partitioning a desired new forwarding behavior all the way down to the forwarding plane. So I don't know that this is exactly how it happened, but I think that we have almost all of the building blocks that we need now, with some purple pieces still to fill in. And this obviously helps create a research agenda for universities to start working on this, and this is indeed what we are doing. So we actually have a program that sort of a research program that we've started recently between ONF and some colleagues, Jen Rexford at Princeton, Larry Peterson and Guru at ONF, and Nate Foster at Cornell, in trying to figure out how we do this verifiable closed-loop control of networks. And so the idea is to build on a lot of the solid building blocks that ONF has today that you've seen already, with the Trellis applications sitting on top of ONOS, the P4 runtime contract, and then over time, as the Stratum OS becomes more widely deployed, P4 into switches, NICs, and into vSwitches, it gives the mean to now take fine-grained per-packet measurement, for example, from INT. There are many research projects that are going on towards this end, not only amongst this group here, there are also at many other universities as well. If you want to learn more about sort of higher-level representation of this measurement, read the Sonata paper from Jen Rexford that was at SIGCOMM last year. Then for generation and verification, if we are to do this, then we need to be able to verify that the code that we're generating actually meets with our original goals. There's very nice work that Nate Foster has been doing at Cornell on something called P4V, which is verifying the correctness of P4 programs prior to deployment so that you know that they meet some set of invariant properties. Ready for prime time? No. But getting there using and enhancing P4, a language that we're all beginning to adopt. So this is something that's sort of in sort of gestation right now as a program, but we're trying to figure out how we move in this direction in order to help these pieces come together over the next few years. So, of course, I would say this. I think of this phase 3 as networks managed by this verifiable closed-loop control. And I would love to work with many of you on how we can get there. What are some of the building blocks and pieces sort of as part of this overall vision? So I do think that the adding to what I'd said back in 2012, we will measure and validate correctness. Then we will generate and verify a code fix, and then download to correct that bug. This is the direction that I think they were going in. And then you're left wondering, OK, what would we do after that? Well, I think it's kind of obvious. We go to the beach, and that's what I plan to do. Thank you.
OK, I guess pretty exciting, huh? So Nick, don't go away if you are willing to take a couple of questions. Maybe, I know we are almost, yeah, I think we have time for a few questions. So anyone have questions for Nick? Don't let him go that easily. Oh, go ahead.
Brian Zonsticker, PowerRocks. Thank you for the presentation overview. Hey, when you were comparing the from the IC to the kind of from a power or energy utilization perspective, as you were comparing the whatever your legacy box or whatever you said to your solution.
Yeah.
I wasn't sure too if you were just comparing your IC to the box and the power state as a per port perspective, but I was wondering, is that literally the I guess peak power consumption of an individual port, or does that include the overhead that's normalized at a per port basis? And I'm just wondering how to separate the apples from oranges.
How was that actually done?
Yeah,
so it was actually much simpler than that. As an equipment vendor posts on their webpage the ratings that they have for their particular product using in that particular use case. This is taken exactly from that webpage from an equipment vendor who had them with both of these types of silicon. So it's trying to get an apples with apples comparison. Because I realized that if I was to do that personally, then where would that come from?
I haven't been someone who built those things. Yeah, I understand. But do we know, even if they list a number in their spec, but do you know where it comes from or how it means? If they're just putting a number on a page, right?
Sure.
But
so
do we know if
it's measured from the specification or the made by the equipment vendor is that if you use that box, what your power consumption will be as a power that you will experience in your network using the particular protocols and software load that they use. Okay. Right. Happy to talk offline on the details of that.
Fair enough. Thank you.
Since you didn't mention it, do you see a role for AI, artificial intelligence?
I'm sorry?
Do you see a role for AI in
AI?
Yeah.
So, let's think about what would be useful with if you were to use either training and then inference of network behavior, whether it's packets, the network state, or the code, in order to try and figure out what your network is doing. There are some things that probably lend themselves quite well to this. Large trends of, for example, in a mobile operator for how things are changing currently that are on such a scale that it's very, very hard to do on a detailed basis. Personally, I don't think that it has a very good role in security because I don't want statistical knowledge about whether my network is secure. I want to actually know that there isn't an infiltration. And so I think that we have to think very carefully about the use of machine learning and AI for managing and controlling networks. Underneath, it is something whose behavior is defined by code that we write. So we already have a model, a design, it's that code, telling us what it should do. We should hold the network against that test, in my opinion, whenever we possibly can. If we really, really can't do that, then okay, maybe rely on statistical observations. But I think that should be a last resort, personally.
Maybe I can ask you a quick question. So when you look at this journey, what are the things that you are surprised that things didn't play out as you had hoped, or things that have surprised you that they've gone faster or better than what you had hoped 10 years ago?
So the very first papers that were written about SDN came from AT&T. And they were very much from the view of how you would change operator software in order to put the operators more in control. And I don't think anyone took it that seriously because it just seemed like an impossible thing to contemplate. Because at that time, all of the systems they were using, the software was proprietary and came from someone else. And so perhaps not surprisingly, it then morphed into being all about the data center companies, armies of software engineers. They were building from the ground up much simpler networks. What didn't happen in the middle there was, what about enterprise networks? What about the networks that we use every day in campuses? And it surprised me, and it continues to surprise me, that this change has not happened there. Now, there's obviously a lot of turmoil going on there because no one's quite sure, should they build out their IT infrastructure in their campus, or do they just move everything to the cloud? So that has sort of muddied the waters. But there's this still kind of big open question. And so I actually thought there would be another 10 years or so before the ISP and the big network operators would kind of get on board, because it's such an enormous, enormous challenge. And so I think that I was actually quite surprised when so many operators got involved with ONF and really started to commit. And we've seen that level of commitment represented today. And for a number of large network operators that are in the room, that really surprised me. And that almost everyone is transforming to having a large software expertise and large software skill in order to do this.
So yeah, very much like the talk. Would you agree that what you've described essentially is a pattern that would apply to things beyond networking? It seems to apply very broadly and sort of towards a zero-touch commercial enterprise position where everything is zero-touch. Do you see that as a bigger picture that this sort of is the underpinning of and maybe the start of?
Well, at some level, if you want to have a closed-loop control system, you have to observe its state in order to be able to modify it. And if its behavior is defined in software and then state, then they're the obvious control points that you have. And so networking is probably much simpler than a general-purpose compute environment in that the desired behavior is much simpler and the state is much more well-defined. So in a way, it's a much easier place to start than it would be in general-purpose compute. But almost any infrastructure that has this behavior, sort of inevitably, most manufacturing control systems already work this way because of their well-defined behavior and the consequences of getting it wrong, and the timescales are much slower. So really, we're just sort of marching on and borrowing from those well-worn lessons from observation and control. But I think that for anyone who's trying to manage an enormous at-scale system, that wherever they can have well-defined behavior that they can observe, check, verify, and correct, then of course you want to do it so you can focus all of your energy and attention on the bits that are harder to manage and control.
Okay, one more question, last one.
Hey, Professor. I'm actually a network engineering student. So I actually wanted to ask you, so I see this trend moving towards more layer of abstraction of protocols, and as you said, maybe a few years down the line, we might actually not know about how protocols are because it's way down abstracted. So as a network engineering student, my question is right now, should we, so it's like having your legs in both vehicles because you don't know where it's actually headed towards. So what is your take on it? How should the current networking engineering students focus on?
Yeah, no, that's a great question, and one I spent a lot of time thinking about. I think there are some sort of principles that they may be either everlasting, or at least they're going to be here for a long time. Things like packet switching, layering, encapsulation, things that we perhaps take for granted, but they're important building blocks of networks. And there are things that you have to do. You have to decide where a packet is going to go. We call it routing. You have to decide what you do when there are too many of them. That's congestion control. And so there are these things that will continue to be these either principles or problems that need addressing that we will change and modify as we learn more. It's just how we will go about it that will change, rather than simulation, go to the IETF, persuade a whole load of people that they should change it, and then 5 years later something shows up. It will be, I'll just go and change a program and see what happens in a small protected part of my network, and then roll it out more broadly if it turns out that it works. So I don't think that the underlying principles will change. Hopefully we don't have to worry so much about learning protocol supery that we've had to do in the past, that we can think more about what it is, the problem that we are trying to solve in our environment. So programming.
Okay, with that, let's thank again Nick. And
Thank you.